In this video, we're going to derive the two-dimensional triangular shape matrix. Notice that I just said shape matrix, not shape vector. Before I do that, I want to clear something up, what I said regarding developing the form of the shape functions and shape vectors for the one-dimensional bar element. What I was trying to say was that there's two ways to get to this form. One way is to say, well, I know that I'm trying to approximate my unknown function, which in this case is the displacement in the x direction, as a linear function. And what defines a linear function is two unknown coefficients, a1 and a2, the y-intercept and the slope of my line. In order to define those in terms of my unknown displacements, u1 and u2, I'm going to pretend for the moment that I do know what u1 and u2 are. I know that u1 is at x equals 0. I know that u2 is at x equals L. That allows me to solve for a1 and a2 in terms of u1 and u2. Once I've done that and I found what a1 and a2 are in terms of u1 and u2, I can do some rearranging so that all of my x dependence is in one vector and all of my dependence on my displacements at the nodes is in another vector. That's one method. The other method is to use something called Lagrange polynomials. In Lagrange polynomials, I assume or I say that this line represents my domain. So this point is L and this point is 0. I can imagine an equation that equals 1 at this point and equals 0 at this point. And it's a linear equation, so it looks like this. And this equation that is 1 at this point and 0 at this point has the form 1 minus x over L. I can assume another equation that is equal to 1 at this point and 0 at this point. The equation for this line is simply x over L. If I would like an equation that equaled u1 at this point and 0 here, and I'm going to assume that my u1 is represented by this height, then I can get this equation by multiplying this equation by u1, which is what I'm doing when I multiply u1 by 1 minus x over L. Likewise, if I assume that this height represents the location or the value for u2, I can get an equation that equals u2 at x equals L and 0 at x equals 0 by multiplying this equation, x over L, by u2. Now what I'd really like is an equation that equals u1 at x equals 0 and equals u2 at x equals 1 as a linear equation. I can get that by adding these two equations multiplied by u1 and u2 together, meaning I'm adding together this green line and this blue line, and that gives me the equation that I'm looking for. And notice that this is a dot product, so that's exactly what that's doing. That'll also give me the shape functions using Lagrange polynomials. All right, now let's set all of that aside and let's start talking about two-dimensional triangular elements. Here, I've drawn a two-dimensional triangular element. It exists in xy space. From my problem statement or from my own decisions of how I'm going to define my grid, I would know the locations of each vertice of my triangle, which is where I will put nodes. Node number 1 at x1, y1, node number 2 at x2, y2, and node number 3 at x3, y3. These would be known once I set up my grid. I'm looking for, or at the end of my problem, I will solve for the displacements in the x direction and displacement in the y direction of node 1, node 2, and node 3. The numbering is important. Notice I'm numbering in a counterclockwise direction. The derivation I'm going through is always going to assume that I'm picking a point as my first node. My second node in the local coordinate system will be in the counterclockwise direction, and the third node will again be in the counterclockwise direction. I could come up with a derivation in the clockwise direction, but it's important to stay consistent. Also, notice I've labeled these as node number 1, node number 2, node number 3. Your textbook might try to be more generic and label this something like node I, node J, and node M, because really this element will exist inside a larger global system with many more elements. It's unlikely that this will be node 1, node 2, and node 3. It doesn't matter how the nodes are numbered, as long as whatever you're saying is the first element, the next element is counterclockwise to it, and so forth. Our goal, of course, is to find an approximate function for the u, the displacement of any point inside this domain for x and y at any point inside my element. Likewise, I want to find a function v, which is the displacement in the y direction at any point inside my element. Like I did in the one-dimensional case, I'm going to assume that if I know the values of the displacements at the nodes, that I can assume any point inside some linear function in terms of x and y. Here I had two unknowns. I had a1 and a2. I needed to define my linear functions. Now I will have 6 unknown coefficients, a1, a2, a3, a4, a5, and a6. Also notice now that I have 2 functions I'm trying to solve for, u and v. It's a common trick in numerical methods that when you have more than one function you're trying to solve for, is to rewrite your 2 scalar functions, and these are scalar functions, I have one output, as a new vector function with multiple outputs. To that end, I'm going to define my unknown that I'll be trying to solve for as my now vector function psi, which is just a 2 by 1 vector where u is the first member of the vector and v is the second member of the vector. I can rewrite these 2 equations here in a matrix vector form, 1xy 0, 0, 0, 0, 0, 0, 1xy times my unknown coefficients. Take a moment to recognize that this system is the same as this system here. My next goal is to find what these unknown coefficients are. In the one-dimensional case, I took my knowledge of what u1 and u2 were and where their locations in space to rewrite a1 through a2 in terms of u1 and u2. I can do the same thing here. I can take, assuming that I know my displacements u1, u2, and u3, and my y displacements, or my displacements in the y direction, v1, v2, and v3, at the vertexes where I know the values of x and y, I end up with 6 equations and 6 unknowns. So now all I need to do is solve for these 6 equations and 6 unknowns to find my a1 through a6s. I'm going to leave a lot of that to just me stating what the solution is, but let me walk you through a little bit of how we get there. In reality, I don't necessarily just have 6 equations and 6 unknowns. I could break this up into 3 equations and 3 unknowns, and another problem with 3 equations and 3 unknowns, because the u values and the v values don't really interact with each other. Just like the u and v, we can think of our coordinates or our axes as separate. So I can solve by my unknown a coefficients I'm looking for by writing these first 3 equations in vector matrix form. Now I can solve for my unknown a coefficients just by taking the inverse of this matrix multiplying it both sides, I will find my vector of A1s through A3s as equaling the inverse of this matrix times my vector of, at this point, I'm pretending like I know what U1, U2, and U3 are. The inverse of this matrix can be written this way, where I will explain what these alpha, betas, and gammas look like and what those are on a few slides from now. This A represents the area of my triangle. Okay? So with that in mind, I'm going to clean up the board a little bit, move this stuff off to the side. I'm going to take this equation here, I'm going to move it to the top so we have a little room to work with. I now have this written just like I have this written before, but now I have a matrix in terms of x and y and my unknown coefficients I want to solve for. What I want to get to is something like this. I want to be able to write my unknown function I'm trying to solve for in terms of shape functions, which in this case, notice that n1, n2, and n3 along this line are only going to be multiplied by u1, u2, and u3, which will yield an approximation for u as a function of x and y. Likewise, n1, n2, and n3 on this row will get multiplied only by v1, v2, and v. That should be a 3. To come up with an approximation of Vx and y. It'll turn out that these shape functions have this form, where each one is a linear polynomial in terms of these alpha, betas, and gammas. I'll show you what these alpha, beta, and gammas are on the next slide, but they will consist of only information about the locations of each vertex. So they only include geometric information, or information about the shape of my element, which is why they're called shape functions. Also note that this is no longer a vector in 2 dimensions now, because I created this psi function where u and v are stacked on top of each other. Rather than being defined as a vector, my shape matrix is now a matrix. It's a 2 by 6. It's going to get multiplied by u, which is a 6 by 1. This should be a lowercase u. It will yield a 2 by 1 vector, which is what I'm looking for. That is 2 by 1 representing my displacement in the x direction, my displacement in the y direction at one individual location in space x and y. All right, a lot of what I just did is derivation. This is what you actually need to know. The unknown function you're going to be trying to solve for is psi. Psi is going to be made up of a shape matrix made up of shape functions n1, n2, and n3, and organized in this way. It'll get multiplied by a displacement vector. u1, v1, u2, v2, u3, and that should have been v3, but I don't want to correct it at this point. n1, n2, and n3 have these forms. To find your alpha, beta, and gammas, there are 9 of them. They are all made up of information, just information about where the vertices are located in space in x and y. So all of these x and y's with subscripts, remember, these are the locations of your vertices where you have the nodes. On some triangular elements, because of the orientation of the element, it may not be clear what is the base and what is the height. So finding the area of the triangle might be a little bit harder than 1/2 times the base times the height. If that's the case, you can find the area of a triangle using this formula. This now gives us our shape functions and the shape of our shape matrix. Now that we can express our unknown function we're trying to solve for in terms of a shape matrix and a displacement vector, we can start looking for ways to express stress and strain using these approximations, and we'll do that in the next video.